Right. Okay. Hello. I'm Kirstine Dale, the Metaverse's Chief AI Officer, and thank you so much for inviting me to come talk to you about AI. I could talk about AI endlessly, and there's a limit to how fascinating other people find it. But I'm hoping for the next 30 minutes, you, like me, might think that it's infinitely fascinating. So it was also particularly nice to be back in Scotland. I was actually born in Dundee. Now I don't sound like I was, but I was born in Dundee, and I did my postgraduate in University of Glasgow, so it's lovely to be back. So I'm going to talk about the AI for the future of weather forecasting. That is an enormous topic. So it's going to be quite a struggle to cover everything in this short period of time. So it's going to be a fair old canter, because I'm quite keen to try and leave a little bit of time at the end for a nice discussion. So hang on in there. We'll get to discussions at the end. So let's have a go. Sorry. Have we moved? Yes. Right. Okay. So I'm going to go for half an hour-ish, but I'm going to do it in 5 parts. So it's going to be a bit of a canter. First of all, I'm going to talk about the backdrop. Then I'm going to talk about the missing Christmas. Then I'm going to talk about how we embed AI across the metaverse, then look to the future, and then conclusion, and hopefully a bit of discussion. Okay, so I will start with, get slides to move. There we go. Some of the terminology I'm going to use. So the basics are that there's lots of different terminology and lots of jargon, and some of it can feel quite alienating, but there's only really 3 terms that I'm going to use today. And there's data science. So data science are all activities to do with the curation, processing, analysis, visualization of data to extract knowledge and provide insights. Data science is basically a multidisciplinary approach that includes mathematics, statistics, and computers, but also critically domain expertise. And in the case of the Met Office, that domain expertise is meteorology. Second term that we're going to use is artificial intelligence, AI. AI is concerned with techniques that learn to mimic human behavior or intelligence. And then machine learning. Machine learning is a large range of techniques and algorithms that allow machines to learn patterns autonomously from data. So those are the only 3 that I think I'm going to use today. So the other thing that people tend to say, oh, is, oh, I don't really like data science. I don't really have anything to do with it in my life. Okay, data science is everywhere. It's all around our lives already. So this morning, if maybe you opened your mobile phone using face recognition, that's data science. If you maybe used Google Maps like I did to find the church, then that's data science. If you asked Alexa or Siri for a weather forecast, which you really shouldn't, just use the Metaverse app, but if you did, then that's data science. So data science is everywhere, and it's kind of around us already. So it's something that we can, it's nothing to be feared or worried about. It's just a new technology that's coming on, and it's around us already. It's already being used. So the backdrop. Okay. So we are in the midst of what is being called an AI revolution. And that revolution is being brought about by 3 factors. First of all, there's an explosion in the amount of environmental data that is available. Secondly, a massive increase in the availability of compute. And thirdly, increasingly sophisticated data science approaches. So that's there I'm talking specifically about machine learning algorithms and some of the, trying to use some of the terms from the previous slide that I said I wouldn't, but that's like deep learning techniques. So those three factors have caused this real acceleration in the adoption and the possibilities of how AI could be used. And then I've got a quote from Kirstine: "Artificial intelligence is the defining opportunity of our generation. It sets the plans for the technology to boost growth." And on the train on the way up, I was thinking, that I'm not sure that quote's really appropriate for giving a talk in Scotland. So I had a quick look, and I've written it down in my handwriting's terrible anyway, and on a wobbly train it was even worse. But I looked, there was a quote from the Scottish Business Minister, which I think is Richard Lockhead, I think. He said, "Scotland is perfectly placed to capitalise on AI's rapid growth." Very good. And it can, and it must be at the heart of this globally important industry. So these are very powerful and very good points that we're seeing about this. So the pace of technology change due to this AI revolution shows absolutely no sign of waning. So for example, I was invited to give this talk about a year ago. And a year ago, I thought, there is no way I'm writing the talk or even thinking about it at the moment, because in a year's time, we'll be in a completely different place. And we absolutely are. Data science years are like, I often say they're a bit like dog years. So a year is like 7 years. So it's basically 7 years since I was asked to give this talk. So quite a lot has happened. Okay, so despite all of these words, all of these different quotes that people say about AI, the bottom line is that as the world's fastest growing deep technology, AI is rewriting the rules of entire technologies and industries. And that includes how we forecast the weather and how we model the climate. And the Met Office is embracing this technology. As a big science organization, a big data organization, it's a very exciting technology that we're really keen to see the development of and the application. And it is applied, it has been applied in all sorts of ways, and I'm just going to cover a few of them this evening. Okay, so this is going to be really familiar to everybody in the room. This is the weather forecasting pipeline. So this is observations through to simulations, then processing and analysis through to predictions. So I've said that the Met Office is a big data organization. So big data is our everyday. On observations, we have 215 billion observations coming through the organization every day. We run 3 million lines of code. Unfortunately, most of it's in Fortran, but you know, that's set to change in the future. And produce 18 terabytes of data a day from the operational and the parallel suite. So what is 18 terabytes of data? That's 18 trillion bytes of data, which in old money that equates to, I think it worked out to be 27,000 music CDs. So that's a lot of data from the organization every single day. And when I first started working in AI at the Met Office, so that's about 8 years ago, we were already applying data science right across that value chain. And I've just put a few examples here. So for example, starting on the left under ops, this is somebody releasing a expendable bathythermic graph. So these are ocean probes, travel down the water column, and they collect data on temperature. It's really, really important that data is robust because it's used for climate records. So we can see how the climate is changing. 50% of those ocean probes lack the metadata on what sort of probes they are, so you can't do the bias correction, which severely limits the value of the data. So we've been using data science approaches to infill some of that missing data and thereby have a more complete record of how the ocean temperature is changing. I'm not going to cover all of them, but moving on to the ones under the on the right-hand side. The waves. Here we have a project which is Official Development Assistance Project, an ODA project, actually in South Africa with the South African Weather Service, where we are using machine learning to predict future wave climatologies. This is really, really important in South Africa, where they have a lot of critical national infrastructure on the coast. So they need to know how the waves might change in the future. What sort of infrastructure do they need to be considering? What sort of planning decisions do they need to be making now? Second one on the right-hand side, that's the maze. We also use machine learning to look at the relationships between temperature, precipitation, and maize yield. And obviously that's very important thinking about food security. That project initially started in China, but there's similar methodology has been applied in several other regions now, including in the UK. So this is what we were doing when I first started working in AI. It was like an exciting tool in the toolkit that was being applied in lots of different ways, lots of different exciting projects, but it wasn't a big coherent picture. So in 2022, we put together what we called a data science framework, but it's kind of a strategy. It's a top-level plan for what we're going to do with data science in Met Office. And it was embedding machine learning and artificial intelligence in weather and climate science and services. And in that plan, we decided that it was great that we had all these exciting applications of AI, but we really needed to put it all together. So in the data science framework, we have 3 pillars. The first pillar is capabilities. And in this, we identified those 4 priority capabilities for the Met Office. And these are the areas that we, through a lot of resource, we look for partnering opportunities, and we try to really hone our skills on these 4 capabilities. And they were discovery and attribution, fusing simulation with data science, which I'll come back to later, but definitely remember that one, fusing simulation with data science, uncertainty and trust, and data to decisions. So we took those were our 4 main capabilities that we were plowing effort in 2022, and arranging all of those projects, the ones that I'm talking about earlier, we're arranging those under the capabilities. We also had a second pillar, which was about people. And this was all to do with attracting and retaining and developing talent. So how do we recruit staff? How do we get data scientists into the office? How do we make sure that they get the training and the support that they need? How do we foster a diverse and representative workforce? Because I won't go into it in a great depth today, but one of the really, really important things about data science is it's obviously only as good as the data. The data needs to be representative of the society. So that we need a diverse workforce collecting that data and identifying how it might be used. And then we also wanted to engage the next generation of data scientists. So how do we get the next generation enthused about using data science for weather and climate science? And then the third pillar was the partnership pillar. So data science moves so fast. There is no way one organization can stay at the forefront of it, which means that you must partner. So we form 3 different types of partners. There's partners within our domain, so within meteorology and climatology. There are partners outside of our domain. So for example, let's think. So groups like Microsoft or IBM or NVIDIA. So they are in a different domain to us, but they have data science skills which are very relevant to us. And then working with other communities, so tapping into existing expertise across the UK through the Met Office Academic Partnership, for example, or through the Momentum Partnership with our international partners, how we co-develop models. So we set the strategy in 2022, published it in September 2022. Christmas was coming. I was feeling pretty good. We'd set a strategy, had a bit of a plan, you know, we'd taken these little green shoots of data science and the application of AI. I was feeling pretty positive about it. We'd you know, I'd done what we'd been asked. We had a strategy. So then we had the missing Christmas. Okay. So in order to explain the missing Christmas, we need to take a step back. This is what is referred to as the quiet revolution. So NWP, numerical weather prediction, so the physics-based approach to weather prediction started around about the 1950s. And since then, it has been steadily improving. When I say steadily, it's been improving about a day a decade. So this graph shows it's a scale on the y-axis, apologies, the label's not come through, time on the x-axis. So you can see that it's just generally all the metrics are getting steadily improving, and that day a decade is largely achieved by things like increasing availability of observations, increasing compute, data assimilation techniques, improvements in the models, and more parameterization. So it's a steady increase. You'd be generally pretty happy with that. The model is steadily getting better. Okay. So in the background to the quiet revolution, which is a steady increase in numerical weather prediction, we had largely big tech organizations using reanalysis data sets, so largely the ERA 5 data sets from the European Centre for Medium Range Forecasting, so from the ECMWF. They were taking that data and developing machine learning models that would predict the weather. That was going on in the background. So we saw, again, I've got on the y-axis skill, on the x-axis, I've got time. And you'll see that the models were getting steadily better. So this is all sort of happening in the background. You know, we're at the Met Office, we're seeing the quiet revolution, we're seeing NWP get better and better. But coming up the inside lane, we're seeing machine learning models starting to get a bit better, but nothing too alarming. But we're definitely keeping an eye on it. And you'll remember I said earlier, see that theme, the second capability, fusing simulations with data science, that was specifically looking at this. So we were already looking at this. Okay. So dramatic music or something now. There we go. That Christmas is my missing Christmas. Okay. So Christmas 2022, 2023. I don't normally get a lot of phone calls from work at home, but my phone was ringing off the hook. I was getting texts all the time, WhatsApps from all sorts of people at the Met Office going, oh my goodness, we've just seen all of these models released. This little cluster that you'll see up top right, all of those models came out about the same time, all about Christmas, thank you very much, all about Christmas. And they showed phenomenal step forwards in how to use machine learning to predict the weather. So I was getting texts going, what's the Met Office going to do? Do you have a plan? Is the Met Office going to produce a machine learning model? Do you even need a Met Office anymore? Now Google can do this forecasting. Is your job in, like, do we need any of you? Do we need forecasters at all? So that was quite an exciting Christmas, and I'm going to say that was my missing Christmas. In my life, I will look back as that's my missing Christmas. And what was actually happening was, and this is another way of showing it, we were seeing these real improvements in these machine learning models, these real step changes in the performance. They were going from something where, yeah, it's quite interesting, they weren't doing badly, but you know, no one was taking it, if I'm brutally honest, no one was taking it that seriously. We were all thinking, yeah, you know, nice, we'll see how this goes, keep an eye on it. But that Christmas, we saw some step changes, and suddenly they became like, this is something that really, really needs more attention and needs more focus. This has to be taken seriously. So I think the other thing that's really important to say here is, although this graph makes it look like, in contrast with the steady improvements you've seen with NWP, the quiet revolution, that nothing on this graph can happen without numerical weather prediction. All machine learning models are standing on the shoulders of numerical weather prediction giants. So they all use data that is produced from numerical weather prediction. There is Some movements in the that are going on in the moment are like increasing use of observations, but all of the models I'm talking about on this slide are all resting on the shoulders of NWP. So that was the missing Christmas. What did we do? Right, came back to work. No Christmas. Came back to work, and early in 2023, we launched the AI for Numerical Weather Prediction program. And this program, you'll recall that I've said that we can't do anything on AI without working in partnership. Well, we chose the Alan Turing Institute, the UK's National Centre for AI and Data Sciences, to be our partner, and together we are co-developing the model FastNet. So FastNet, obviously named after one of the shipping zones, also quite nicely has the word net in it. So our model is called FastNet. So when designing the AI for NWP program, we set it up to contain 4 projects, which form 2 work streams. Okay, so the 4 projects is the blocky diagram on the right-hand side. There, each work stream, each stream uses 3 projects, and to be really efficient, because don't forget, these models, we're playing a bit of catch up when we started AI for NWP, so we need to move fast. So we needed to design a model that was going to enable us to really accelerate. So everything that we do has to have multiple uses. So we set up the program like this. So input data sets, which is about pulling together the training data that can be used to develop a machine learning model. Then on stream A, which is the one that runs along the top, so that's the blue, purple, and the grey. The purple project was FastNet development, so that's development of the Turing Met-Office machine learning model. And model agnostic infrastructure, so that's once you've developed a machine learning model, how do you embed it into the forecasting workflow, which turns out really a lot more complicated than you might think. So that project's actually a lot bigger than it looks on this diagram. Then the second work stream was, it's very exciting that we're developing the FastNet model, but what if the FastNet model doesn't perform as well as we need it to? So I think it's really important that we consider other machine learning models. So the other work stream, again, takes input data sets, but it looks at machine learning models that have been developed elsewhere. So I think last time I counted, there was about 16 different machine learning models. In a machine learning model in comparison, we're not looking at all 16, but we're looking at a small subset. But we're looking at different models and evaluating their performance, not only against traditional physics-based models, so NWP, but also against FastNet. So we can see, well, how is FastNet performing compared to the other machine learning models, and how is FastNet performing compared to NWP? Yeah, okay. So a little bit more about FastNet. So FastNet, as I've already said, co-developed with the Alan Turing Institute. It is a global atmosphere model. We're developing a high resolution capability. So we eventually will be, I say eventually, not in the next few months, hopefully we will be looking at and using UKV data, which is the high resolution UK data. It produces a forecast out to 14 days. It exploits unique Met-Office data assets like UKV, and we are trying to move towards how might you operationalize a machine learning model, not as an alternative to NWP, but as a complement to NWP. Now, I think this one should move. Yeah, there we go. So is FastNet any good? Yeah, it is quite good. It's not as good as it's going to be. As soon as we get the UKV data in, I'm expecting there to be a step change in the performance of FastNet, but it's performing at the moment. So the FastNet global forecast performance is now comparable to the Met-Office's global model for root mean square error on some of the WMA metrics. The images on the right-hand side, I think, yes, on On the left, we have the global truth model, the global truth, and on the right, we have FastNet model. So it's quite difficult to see on this sort of scale, but there is a bit of smoothing because of the way that the model is set up, because it's trying to minimize root mean square areas. So there's a bit of smoothing. Smoothing, obviously not a good thing because you don't want to lose fronts, because the fronts are quite important. So this is a feature of quite a lot of machine learning models. It's also a feature of FastNet, so we'll be looking at that. However, this model has been developed very quickly, and it's performing already. So very pleased with this model. And like I say, I'm hoping that we see some step changes in it in the next couple of months. So what about the next steps for the FastNet model? Should I just keep an eye on the time, make sure I keep enough time? We will be addressing spectral biases, looking at that smoothing feature that I've already mentioned. I'm not going to read the slides, it's going to be taking too long, but we will be trying to get it down to do high resolution, so over the UK, get that model performing, sort out any smoothing issues. Okay, so I kind of hinted before that this is not a replacement to numerical weather prediction. This is really often asked about this, especially by forecasters in the Met Office. You know, are you producing a machine learning model that's going to take the place of NWP? No, this is just the next step for numerical weather prediction. So this is on our website at the moment. On my list of things to do is to talk to the comms team. I really want them to add a little bit of text now. So we need another bullet at the bottom, which talks about how machine learning can help with NWP and take it on the next step forward. So in the long run, we expect that machine learning models and physics-based models are going to run alongside one another, that they will mitigate one another's shortcomings and amplify each other's strengths. So what do they actually bring to the party? So physics-based models bring physics process-based insight, which is absolutely critical if you need to build understanding and trust. They also produce all of the training data used to create AI models, and that's going to have to be recalibrated as the climate changes. And they are essential when considering events that are outside the data. So machine learning models can predict events that they've experienced from their training data. If it's an event that is outside their training data, then that won't be something that they can forecast. So, for example, when Mount Pinatubo went up in 1991, released all the aerosols up into the atmosphere, that would have been outside of the training data of a machine learning model. So a machine learning model wouldn't have been able to cope very well with that. That's NWP, but what does AI bring to the party? Okay, AI models they're not just a little bit fast, they are astonishingly fast. They are tens of thousands of times faster, which means that they use considerably less compute, which means that they produce less CO2, which means that they can be run much closer to real time. Their speed and accuracy but basically their skill and their accuracy is the big advantages of machine learning models. So with this approach, we're seeing a new paradigm for weather prediction. So next, I wanted to change tack slightly and talk very briefly about embedding AI across the Met Office. So I've only really talked about using AI for weather prediction, but obviously the opportunity for using AI stretches across all of the Met Office's operations. So in the background, so we've produced that strategy, which we really had to accelerate really, really fast after the missing Christmas. But in terms of implementing the whole strategy, we've also launched a new program, which was only launched last year, but in dog years, that's like 7 years ago, called the AI for Everyone program. So AI for Everyone is basically structured to cover everything that the Met Office does. So there is AI for enabling. enabling our like corporate functions in the Met Office. So it includes things like HR or the library or finance or the legal team or any back office function. Then there's AI for national capability, and that's our bedrock science. And that's where the AI for NWP project fits, for example. And then there's AI for products and services. So how might you apply AI in order to deliver products and services, so to go the last mile to provide customers and users and sponsors with the information that they really want. People seldom want to weather forecast. What they want to know is how is that weather going to implement what they're trying to do. So we are now arranging all of the projects and all of the activities and all of our resources according to these 3 areas. And I've just listed some of the examples on this because this slide became way too busy, but it's still pretty busy when I put it all on. But so we have within, let's start with AI for national capability. We have the AI for NWP project. So that's the project that we're developing the FastNet model with the Turing Institute. We also have a project looking at AI for digital twins. So that's called the TWINE program. We have another program which is AI for climate, and that's looking at how might you use climate AI in climate modeling. Really exciting there. So we could be using AI to do downscaling. Climate models are generally quite coarse resolution. Getting them down to the fine scale that you really want uses a lot of compute. If we were able to do that with AI, then this would be a great step forward and make those sorts of forecasts a lot more accessible. Let's do AI for products and services. So this is an area that I think will be a bit of a focus for the next 12 months. We really need to be engaging a little bit more with users and people who are actually using the forecast to make decisions, to make sure that they're getting the information they want in the format that they want, and have a look at how we might use AI to help with that. On the enabling side of things, so enabling anyone who works in the Met Office, so anybody who walks through the front door or logs on from home, uses AI. So we have Microsoft 365, which helps everybody in their day-to-day work. So we all use all sorts of like chatbots, all sorts of things to make our lives much easier and to enable freeing up time so we can focus on things that are really adding value. And we also have access to GitHub Copilots, so that's to help our staff with programming. And then in the middle, the AI for everyone, which doesn't really, the size isn't representative of how big an activity this is. This is really, AI for everyone is really what would probably be described as a change program. So here we are trying to raise awareness and understanding of how AI can be used and to generate some enthusiasm for embracing these tools. And we did that through a set of things like we have a seminar series, which we have people coming in to talk to us, which I'm doing now for you, to enthuse people about using AI in science and science discovery. We also have a community of practice, and I think there's about 20% of the organisation are members of the community of practice, which is great. And we run lots of events and stuff. So there's a lot of support that goes, that's channeled through that central area, and training and lots of things to support the data science framework in the people and the partnership pillar. So what about looking to the future? So we will continue to develop AI tools and skills. We've got the partnership with the Alan Turing Institute. We are also, as I've already mentioned, developing the FastNet model. We're building understanding and trust in machine learning models, not only in FastNet for numerical weather prediction, but also having a look at how we might be using AI for climate modeling. There's a really big focus at the moment on skills development. So not only supporting staff and moving in to start using AI a bit more, but providing them with training opportunities, partnering opportunities with different organizations. And we are focusing on building international partnerships to tackle the challenge of foundational models and climate models. So there's a lot of activity going on to try and make sure that we have the partnerships. We need to work very closely with ECMWF, for example, who are a real leader in how to use AI in this space. We're also looking at compute and the data ecosystem at the Met Office. We're building the next generation modeling and compute platform. So yeah, put a picture up there of the new computer. A lot more exciting than it looks. We're leveraging cloud and hyperscale technology, which is obviously a lot more suited to AI. And we're developing our data sets so that they are fully available and usable for training the ML models. Obviously, very challenging to do this all at once. No one was going to escape from an AI presentation without like a generative AI image. So here's my Gen AI image. We are looking to find how AI might fit on the team. It is not the replacement for the team. It has just got a role on the team. And what we're trying to do is scope out how can we best use AI to complement what we're already doing so that we continue to offer the best possible forecasts. So there we go. We're committed to continuing to use the best data and the best data from the best models, wherever it comes from. And that may well be blending data from multiple providers, all validated and secured appropriately. So bringing together data science techniques with traditional numerical weather prediction physics-based approaches. So just one more slide now. In conclusion, we can see really exciting potential for AI, but this needs to ensure that the physics-based approaches remain at the heart of our technology. Physics is the DNA of weather forecasting. I don't see an end to that anytime soon. I certainly don't consider AI to be an alternative. It is absolutely a complement. So we are looking to build Met-Office skills and experience. Increasingly, that means working with partners, because as I say, it is impossible to stay at the forefront of this technology. It's moving too fast. And we are embedding as appropriate so that we are using the best data for the right purpose. Thank you.
Thank you, Kirstine. It was fascinating and great to see all the advancements. We'll take a little bit of a Q&A. Hopefully we get the questions from the audience. I'll try and manage it between online and in-house. I usually kick off with a question myself.
Okay.
So my background's in forecasting and operational meteorology. How a big part of, you sort of made a passing comment about keeping us all in jobs or not in jobs. It's kind of a big point. A big part of being in operational meteorology is understanding the characteristics of each of the models and sort of knowing when to add value and how to add value. How does an operational meteorologist fit in with AI when you perhaps, I'm guessing, that you have slightly less understanding of the background physics or not physics?
Okay. So that's kind of in two parts. How do the operation meteorologists fit in? Well, we are bringing operation meteorologists on the journey with us. It's really essential that they're involved from the get-go. So, for example, every Monday there's a meeting which involves operation meteorologists looking at how the machine learning models have been performing and comparing that with how numerical weather prediction has been performing. And we're really trying to draw on their technical expertise to make sure that the machine learning models are validated and developing how we think is appropriate. What was the second part?
So how do we use that in an operational sphere? You know the characteristics of certain models and you can sort of learn when to trust them or not to trust them. Is the game change a bit?
The black box thing.
Yeah.
So we are trying not to let AI and FastNet become a black box. We are trying to make sure that we maximize opportunities to understand how the model's performing, how it is performing. And there are techniques called explainable AI, and we're looking to embed those into the development of FastNet. So it's not black boxing it.
That's good.
But this is definitely a work in progress.
Thank you. Hands going up. Well, we've had a couple. I've asked my meta questions, so we'll go on the front row. Who goes first?
Yeah, sure. There was just a kind of a brief passing comment about using AI for climate research, but it seems that given that it can only work off of historical data, essentially, or train off of historical data, are they useful or will they be useful in climate change research?
Wow, this is a really great question, and that's what we're looking into at the moment. So I think that AI for numerical weather prediction, despite the missing Christmas and the slightly faltering start, we've done a good job catching up now, and I feel really confident about how FastNet's going to perform this year. AI for climate is really only starting to take form now, so we're really it's kind of where we were with weather about a year ago. So we're trying to form like what's the best approach. So there's two projects that are currently underway. One which is looking at AI for downscaling, which is I think a really exciting area, and the second area is to look at foundation models and other data-driven approaches, which I think is where your question really comes in. I think it's probably too early to say. It's a bit early to say, but maybe I'll come back in a year.
So give it a year, and I'm sure.
Yeah, a year, 7 years. Yeah, I'll come back.
Thank you.
Where am I? Yeah, point to that.
Hi, Kirsten. Another Met Office question here. I'm a forecaster, but also do some international work with the Met Office. So I've been involved in nowcasting projects in Southern Africa, but I was just wondering what we're doing for sort of nowcasting convection at the Met Office for this country, effectively.
So not as much as if you ask me in a year's time. Okay, so this is, at the moment, we're formulating the plans for what the focus is going to be for the next 12 months. We're going through the budgeting process and like trying to allocate stuff. Don't forget that as much as I've been working in data science for quite a long time and the Met Office has been doing little bits, this is quite a big change for the Met Office to be embracing this as fully as it's going to need to. And that means that staff are retraining and upskilling, and so there's a lot of change going on at the moment. So we're not able to do as much as I would like us to do instantly, but this year we will be looking more at nowcasting. So nowcasting is in the top 5. So
excellent. And convection.
This
Thank you.
Next year, hopefully, we'll have a lot more to say on that.
Questions on the screen person from the ones that are on line. The top one's a kind of coverall question in this instance. Is how is the Met Office making FastNet explainable and interpretable? Is physics embedded anyway? So I guess.
We're still working on that at the moment. I can't go into the details, but we're looking to make it explainable so that we don't want to have a black box model. So it's not. There are standard practices and approaches through explainable AI. So we've got some projects. We've got one particular project with the University of Exeter, which is going to be looking at how might we develop FastNet so that it is explainable, because the community that we engage with want to understand the models. It's not enough just to see whether the forecast's good or bad. If you want to build trust, they really need to understand it. So we're looking at these different techniques to try and figure out what's going to be the most appropriate for FastNet. But watch this space, hopefully, more soon.
Yeah, Jeff, you had one, and I'll move next through.
You mentioned about somewhere on one of your slides about, and I think you spoke, AI being very accurate. I'm wondering if you might say a little more. I mean, are we talking about 2 days, 3 days? Is there a drop off after so many days? Presumably, most verification is done against 500 millibars or something. Some of us live on the surface. You know, I'm just wondering whether you might say a little bit more about those issues.
So I read a really amazing paper on the way up on the train about the accuracy of machine learning models that I'll be happy to share with you afterwards. But I think you're right to ask me about the drop off. Machine learning models, it can drift a bit, so there's a bit of bias that comes in. So it's on the shorter timescale, they're usually a bit more reliable, which makes the climate timescales a bit more challenging. Going back to the other question, so we're seeing a bit more stability in some of the most recent models. So one of the most recent models is called Neural GCM, which is another Google model. That has got a bit more stability in it, and that seems to be lasting beyond just a couple of days, which is really encouraging. I think when looking at the machine learning models, it's easy to identify things that maybe they don't do so well on. So one of the front runners for machine learning models was the Pangu model, but it didn't have precipitation, and obviously everyone cares about precipitation. So that was a bit of a shortfalling. But all of those models, I think it's easy to identify the things that they're not doing well now, but I bet they will do. If it keeps accelerating and progressing at the rate it is, then all of the hurdles that we're identifying now, all of the shortcomings that we're identifying now will be overcome. So they are getting more accurate, more reliable in terms of timescale, and they are getting better precision. So for example, we used, there's a project that was between, let's say, University of Reading and Bureau of Meteorology in Australia and the Met Office, where we're using machine learning to, I think the paper was published last summer, it was downscaling temperature forecasts, I think it's temperature, from 1.5 kilometre down to 100 metres, which is great. And it shows remarkable skill, and that's from the site, and that uses a tiny fraction of the compute. So I think one of the questions that we're going to have to face quite soon is, how good is good enough for a forecast? Like, how much accuracy do you really need to inform different types of decisions? And it may well be that for certain types of decisions, and machine learning forecasts that can go really, really fast and really, really cheaply in terms of compute and CO2, that might be the way forward. Whereas for something like a decision on should you open Heathrow, that's clearly going to need a bit more precision and accuracy. You're going to want to understand that. That may well be something that NWP is more appropriate for.
So can I just add a quick rider? So what you're perhaps saying is that at the moment, the big potential for AI is perhaps 1, 2, 3 days, whereas perhaps the standard EC or global model from any of the centers is probably still better at longer range. Might that be a conclusion?
I would be, I'd be nervous about making any bold statements, right, because whereas today it might be accurate for more, not as accurate for as an EC model for 14 days. In a year's time, who knows? Who knows? It's progressing really fast.
Thank you very much.
Yeah, I'll move across the room. Whilst I do that, there was hopefully slightly, the question hopefully was about, is I look about the physics and maybe their output, is it being used to produce text-based forecasts?
Oh, really good question. Well, Fastnet's not, obviously, but we are looking at how large language models might be used for text-based services. But that's very much on starting blogs. We've had some meetings recently to talk about what we might do in that space. But I think large language models show enormous potential, and there's a lot of text-based services in the Met Office. So really excited to see where that might go in the next year. I feel like every question I'm saying, not yet. Invite me back in a year, but you know, I'm keen to get back to Scotland. So you invite me back.
The value of a forecast does depend on the weather, of course. So how do these compare for example, the named storms or major droughts?
So there was a study last year, I think it was. Feels like a long time ago, but it probably wasn't. I think it was last year, looking at Storm Kieran and how the machine learning models performed against that. And at the time, the models at that stage, though they're better now, but at that stage, they did quite well in forecasting wear, but not intensity. So intensity is something that's been flagged as an area that's the machine learning models are not performing as well. But this is something that's being looked at, and like I say, I reckon give it a short amount of time and that they'll be doing fine. At the Met Office, we're also doing some work to have a look at how the machine learning models are performing against more extreme events, like for example, heat waves or flooding events. But that work's underway. I haven't got any conclusions on that one just yet. But intensity is one of the areas machine learning models, and well, this time last year they weren't performing as well as MWP models.
Thank you. How time flies when you're having fun with a Q&A. We'll take one more. Was there one at the back? Zane, nothing to. Yeah, it's just for the guys online, so they can get a question.
Hi, it was a very well-wrapped presentation to begin with, but I just wanted to ask, you mentioned there were a lot of steps between each of the new and upcoming weather models, but do you, and I think the first question mentioned the black box problem. Do we know what is causing or what causes the steps in accuracy between maybe not FastNet, but the previous models?
Well, previous model, like the step, you mean why is there like these big
Right, so what's causing the steps? Yeah.
Well, quite a few of those early models, they were using different architectures. So they were different types of models. So some of them were graph neural nets, some were transformers, and the different approaches showed different levels of performance. I think now it seems to be the jump doesn't, well, who knows, but at the moment we're not seeing those big jumps that we saw at the very beginning, but I think that's fairly standard for a new technology, or not new, but for an emerging technology. You see these big jumps at the beginning and then it kind of levels off a wee bit, but I think it was most of the big changes at the beginning were down to different architectures.
Thank you. That's us for the Q&A. Thank you so much again for coming up to visit us, and apologies for the slight IT technicalities. So once again, please thank you. As I say, that concludes our season of talks for this